In this video, I want to continue in our review of ME 3200. Last time we took a look at Chapter 1 and Chapter 2. I'm going to go ahead and share my screen and go to the document that I have put on Blackboard of the review of 3200 of PDF. And so in Chapter 3 is where we learned how to determine the thermodynamic properties associated with the substances that we will be using in our thermodynamic analysis. In this particular chapter, you recognize or you learn that substances can exist in various phases: solid, liquid, and gas. We also recognize that some thermodynamic substances can actually occupy or be in two phases, 2 or 3 phases. And so in this particular chapter, they bring up the concept of a pure substance. A pure substance is nothing more than just the same substance. When we talk about water, it's all just water. We aren't looking at mixtures of 2 different substances. We may look at mixtures of 2 phases of the same substance, but a pure substance is one that is only a single molecule or atom. The state principle basically stated that when you did have a pure substance, it was necessary to be able to identify 2 independent thermodynamic properties. Upon identifying 2 independent thermodynamic properties, one then knows or can determine all the other thermodynamic properties. So that will be very important in our calculation or our determination of the various thermodynamic properties for the pure substances that we will be treating. We will be, in this chapter, we will be looking at pressure, volume, temperature, surfaces. Pressure, volume, temperature, I always say, are the big 3 in thermodynamics, because those are the 3 thermodynamic properties that are easily measured. It's easy to measure a pressure, it's easy to measure a temperature, and again, one can also determine the volume associated with a certain amount of a substance. Phase diagrams, we'll be looking at the phase diagram associated with various pure substances. And the phase diagram then will dictate which phases are present at a given thermodynamic equilibrium point. As we talked about the pure substances, one of the most important things to recognize is that substances have a saturation temperature associated with them, as well as a saturation pressure. And these saturation pressures and temperatures are typically referred to as the pressure and temperature for which a pure substance goes through the 2-phase process between liquid and vapor. Typically, we will be dealing with just that particular saturation 2-phase process, even though there are other types of processes, sublimation and solidification, where we are going between 2 phases such as solid and gas or solid and liquid. Primarily, we will be discussing the saturation process between the 2 phases of liquid vapor, a liquid vapor mixture. And so when we plot on a 3-dimensional diagram of a surface representing the pressure, volume, and temperature points associated with a pure substance, we recognize that we can cut this 3-dimensional surface and look at just a 2-dimensional diagram. If we cut the surface at a given temperature, we then would have a pressure volume diagram. If we cut the surface at a given pressure, we would then represent that cut as a temperature volume diagram. So most of the times in thermodynamics, we will look at just two properties, and on that diagram would be a indication of the third property associated with that particular pure substance. In two-phase liquid vapor mixtures, there is a quality that we define, and that tells us how far the substance is between the liquid line and the vapor line. When we are all liquid, we say that the quality is equal to 0. When it's all vapor, we say the quality is equal to 1 or 100%. Anything above that, it's superheated. Anything below that particular point, it's all liquid. We will also define the enthalpy associated with the substance, as well as other properties such as internal energy, specific volume, and pressures. We will also introduce a concept referred to as the specific heats. And again, the specific heats are functions of temperature and pressure, and they tell us something about how the enthalpy and the internal energy change as we change temperature. So the key equations in this chapter is the first equation is the definition of the quality, and the quality is just defined as the mass of the vapor in a two-phase mixture divided by the total mass. And so you can see from this equation, this ratio, that if it's all vapor, then we see that the mass of the liquid is equal to 0 and our quality is equal to 1. If it's all liquid and the mass of vapor is equal to 0, then we have a quality equal to 0. And somewhere in between then is the percentage. In this particular case, you see that it's a fraction of vapor over the total. Okay. Go through the dome, the total mixture of liquid and vapor stays the same, but the vapor content will increase as you go toward the right-handed side of the dome. Once you then know the location of that point on the saturation line, that then allows us to determine the thermodynamic properties across the saturation line. The thermodynamic property of the specific volume, the internal energy, as well as the enthalpy. Each of these are then just related to the volume, internal energy, and enthalpy at the liquid point, which is all the way to the left, times this ratio, this fraction of the range across the dome, the specific volume, internal energy, and enthalpy at the saturation liquid point or vapor point minus the same at the saturation liquid point. And so it's basically, we define the point on the line by giving a particular quality as well as a temperature or a pressure associated with that line. The key to this two-phase mixture process is that temperature and pressure are not independent of each other. Once one assigns a pressure, the substance will go through the two-phase process at a given temperature. Likewise, once you assume a temperature that the two-phase process occurring, there is one and only one pressure that process can occur. And so in order to have a state identification, we have to have two independent thermodynamic properties. One would be either the temperature or the pressure, and the second would be either the quality or anything else that's defined from that quantity. So if I had a pressure and a volume, I could then know where I'm at on the thermodynamic surface. One of the things that we discovered when we started looking at these properties for the liquid and the vapor phase, we found that the liquid properties did not have a strong pressure dependency. And so when we are in the liquid phase, because of the pressure the temperature that we define, if the pressure is such that we know that it is above the saturation pressure, which means it's forced into the liquid phase, we can say to a fairly good approximation that the liquid properties are only a function of that saturation temperature, that temperature at the saturation point. And so there's very little dependency on pressure for those particular variables. And we'll use that throughout. If we remove ourselves far enough away from the ideal, from the dome, we get into a region, a superheated region that we can designate as behaving as an ideal gas. Gas and vapor are two terms that are used simultaneously. Vapor, though, implies that it could be very close to the dome, whereas gas is usually used when we are far removed from the dome. And so if we're far enough removed from the dome because of the temperature and pressure assigned to the substance, we can assume that the substance behaves as an ideal gas. And what that allows us to do is to have a very simple equation, probably one that you saw back in high school, for the relationship between pressure, volume, and temperature. And that was the ideal gas model. The pressure, the specific volume, the temperature in absolute temperature units, and a constant of proportionality related to the gas in question, the gas constant, the specific gas constant. Whenever we have an ideal gas model, then we also know that the internal energy and the enthalpy are typically only a function of temperature and not as a function of pressure. And so we only need the one independent property associated with it in order to define the other properties being the internal energy and the enthalpy. And so we have that relationship. We also know that enthalpy is related to the internal energy plus a PV constant, a PV value, and we know from the ideal gas law that PV is just equal to RT. And so even though enthalpy appears as if it has a pressure dependency through the PV process, since it's an ideal gas, PV is just directly related to RT, and so we can then say that enthalpy is only a function of temperature when it is an ideal gas. The other two properties that we identify in this chapter are what are referred to as specific constants, specific heats. There is a specific heat at constant volume and a specific heat at constant pressure. Both of those for ideal gases are a function of temperature. And because they are a function of temperature, if we wanted to determine the change in internal energy between two temperatures, we have to perform an integration of CV with respect to dt, because CV is just really defined as the change in internal energy with respect to temperature in a constant volume process. And so if we knew this relationship here, we then can perform the integration from temperature 1 to temperature 2 and get the change in the internal energy. If we assume that the temperature doesn't change too drastic, or the C sub V is not a very strong function of temperature, we can say that it's a constant. And if this is a constant, the integrand then can come out, and we can then perform the integration of just the dt, which is just the change in the temperature. So if we assume we have a constant value of CV, we then can say that the change in internal energy is simply just CV times the change in temperature. Enthalpy, on the other hand, is a function of specific heat at constant pressure, which is a function of temperature. Again, the change in the enthalpy can be determined from a integration from temperature 1 to temperature 2. Again, if C sub P does not vary much, or because the temperature doesn't change much, or the relationship, the C sub B is C sub P is relatively constant, we can pull it out of the integral and have a similar expression where the change in enthalpy is just simply the C sub P constant times the difference in temperature. And so when we start using the software for this class, we are going to have to ask ourselves, is the substance at hand at the various equilibrium points, does it behave as a phase change substance? And if it behaves as a phase change substance at a temperature and pressure, we're going to be using the software to determine all of the thermodynamic properties, even considering it under the dome as it goes through the two-phase process, then going into the superheated region. If our substance is such that we can believe that it stays in the ideal gas region, we then have other relationships that are used to determine the other thermodynamic properties. Okay, I'm going to stop at this point. The next chapter we're going to look at, chapter 4, is where we start looking at the conservation of mass and the conservation of energy associated with a flowing system. So we'll pick up here next time.